Yeah, industry. Today's topic will be Fourier transformation. Another transformation, which is Fourier transformation. Now, let's say we have a function. Let's say function fx, f is a function of variable x, is given in interval from minus infinity to plus infinity. So this is domain of function. Function has a domain from minus infinity to plus infinity. Then we define its Fourier transformation. Let me by f denote the Fourier transformation of function fx. It will be new function of function variable alpha. Variable alpha. Alpha is also from minus infinity to plus infinity. Okay. This function is defined like this. It is integral from minus infinity to plus infinity fx times exponential iota x alpha dx. So you just put here function, given function fx, multiply to exponential function, exponential iota x alpha. Then integrate respect to x. When you integrate, x will disappear because it is Diamond variable of integration. The result will be function of alpha. The result will be depending on alpha. And sometimes it's denoted by f capital alpha. Say f is f for f, right? If you have function g, then transformation will be g capital and g alpha. It's a new function, so we will call it Fourier image of function fx. And if you know f alpha, you can restore original function. So we have also inverse transformation. Inverse transformation, let me denote by f power minus 1, f alpha. It's acting on image function, right? F alpha. And the result is a function of x. It is equal. So inverse function, inverse transformation is given like this: 1/2 pi integral from minus infinity to plus infinity f alpha exponential minus iota x alpha d alpha. So this should be, of course, in most cases, it will be equal to fx. It should be fx. Just is the main question. So if you know fx, you can find its Fourier image, which is f capital alpha. And if you know image, if you want to find original function, then you apply for image for f capital alpha, inverse transformation like this, using this formula, and you will get fx, original function. If you look at these two definitions, both are definitions. If you look at these two definitions, they're very similar. Integral, improper integral from minus infinity to plus infinity, and both is exponential. Only difference is first integral has a plus iota. Here we have minus iota, that's the difference. And also we have this constant, 1/2 pi. In some books, they write in both integral, in some textbooks, they write in both 1/2 pi. Instead of writing 1/2 pi, they used to write 1/√2 pi. They write this one in here in Fourier transformation, and inverse also. They write the same. So it means 1/2 pi, they distribute into integrals. But we are not going to do this. Even some books used to write 1/2 pi here on definition of Fourier transformation. Then inverse transformation is coefficient 1. So, but we will use this definition. It's easy, but to remember, because now it's really easy to express original transformation, Fourier transformation. Let's see. First, see some example of transformation. Okay. This example. let's say we have a function fx is equal some constant, let's say u0, some constant u0 if x is by absolute value is less than 1. What does it mean x absolute by absolute value less than 1? It means x is actually from -1 to 1, right? So and it is 0 if x by absolute value more than 1. So it means if x is, you can write equality here or equality here, doesn't. So it means that if x is outside of this interval, then it is 0. So now what is the Fourier image? Fourier image of this function. Let's find the Fourier image of this function. It is the integral from -infinity plus infinity fx exponenta iota alpha x dx, right? And if you substitute f, so integral actually from -infinity to plus infinity, then this integral became from -1 to plus, because f is outside of interval from -1 to 1 is 0. So integral will be not from -infinity to plus infinity. It will be integral from -1 to 1. So fx is now in this interval is 0. Outside of this interval, f no 0, right? So exponenta iota alpha x dx. Okay, just substitute fx. Then what we do is we just u0 can write outside. If you write u0 outside, then what will happen? Antiderivative of exponenta is exponenta. So antiderivative of function exponenta is exponenta. So you must divide to this iota alpha from antiderivative, right? Then you should substitute -1 and 1 to x. Then it's equal u0. If you substitute 1, this will be exponenta iota alpha minus, when you substitute -1, it will be iota minus iota alpha when x is -1, or iota alpha. And you can use here Euler's formula. Let me write here Euler's formula using different color. So we'll use several times. What is the Euler's formula? Just remind you Euler's formula from Math 1. Let me remind you Euler's formula. Iota alpha is equal cosine alpha plus iota sine alpha, right? This complex number is, you can write like this. Cosine alpha is this complex expression of this exponent, right? So, and also you can see from this, it follows that absolute value of this is equal root of cosine square alpha plus sine square alpha, which is equal 1.
Sir, someone is asking class.
Okay, let's check. No, it's joined already. Okay. Okay. Let me change the color. So then if you use this formula, Euler's formula, for both exponent iota alpha, exponent to this, you will get this one, u0. First is cosine alpha plus iota sine alpha, right? Second one is minus cosine alpha minus iota sine alpha, right? And then our iota alpha, so which is equal. So what will the result? Will be 2u0, just 2 times sine, 2u0 sine alpha or alpha. That's all. So this is the image of this function. So this function is also known as box function. They call it box function. So Fourier image of box function is this 2u0 sine alpha or alpha. If you want to see graph, let me first draw the graph of original function, which is a box function. Box function has this graph. Okay. So from -1 to 1, it is equal u0. Let be this is u0. Then graph of this box function is like this. It is equal to u0 when x is from -1 to 1. Then it is 0. They call it box because you can close. If you close like this, so it will be something like box. Box. So this is box function. Box function is discontinuous function. If you have signal which is discontinuous, it's not good. But what is the image? So this is the fx, right? This is the fx. Now let's say what is the image? Image, this one. Let me try to draw the graph of the image. Okay. Let's say this is alpha axis. Okay. Okay, let me, this level is 2u0, or maybe not this level. Okay. This level is 2u0. Okay. And let me remind you from calculus, limit when alpha goes to 0, sine alpha or alpha. So how you find sine alpha or alpha when alpha is 0? Because sine 0 is 0, alpha is 0. It is 0 over 0, right? If you use L'Hopital rule, the derivative of sine alpha, cosine alpha, derivative of alpha is 1. So denominator will be 1. Numerator will be cosine alpha when alpha is 0, limit is equal 1. So this limit is equal 1. So it means when alpha is equal 0, this function is equal to u0 because sine alpha or alpha is 1. So the result will be 2u0. Then what will happen after this? When alpha equals 0, we found that it is equal, function is equal to u0. Then what will happen after this? What's the job done by sine alpha? Sine alpha, everybody knows the graph of sine alpha. It is oscillating, right? From -1 to 1, sine alpha is oscillating. What's the job done by this alpha in the denominator? It is damping. You have a signal, sine alpha, and it is damping by 1 over alpha. So it will be graph like this. You have 2 here, then it is sine, and it is oscillating because of sine, and it is damping. The same to the left side, the same, because sine is defined for all, right? It should be symmetric. I will try to draw it symmetric, but you must understand that it is symmetric. So this is a graph of f capital alpha. Clear? This is the image of the box function. Image of the box function. So what job done in this case for this signal? Box is discontinuous signal. It is transforming to the very smooth signal, which is damping at infinity, right? Very smooth signal. Sine alpha, it's very smooth. Okay. Somebody coming, right? Okay, admit. Done. Now, what is the relation between this transformation and derivatives? We must know this because we want to apply this transformation for the solution of PDEs, right? So now, let's say we finish with this exercise, okay, example. Now, let's say function fx vanishing at infinity, at x minus or plus infinity. Okay, it's vanishing, it's 0. Now, and let's say and it has derivative. Derivative f prime exists. Okay, it is differentiable function. Now, So question is, what is Fourier transformation of the derivative? Fourier transformation of the derivative. So what will be the action of this Fourier transformation on this derivative, right? Let's check. What is, by definition, Fourier transformation for any function, it is integral from minus infinity to plus infinity. Now I must bring here function. Function is f prime x, right? F prime x exponential iota alpha x dx, right? So now we use very simple formula for differential. What is the differential function? Df x is equal, by definition, differential is derivative times dx, right? So derivative times dx is df. So it means this, I have derivative dx. This is dfx, right? So now I can write this integral in the form equal exponential iota alpha x dfx. So now this integral is ready for application of integration by part, right? So if I write formula for integration by part, it looks like this. From iota alpha fx from minus infinity to plus infinity minus integral from minus infinity to plus infinity fx differential of this iota alpha x. Clear? It's just formula for integration by part. So first term is 0. Why first term is 0? Because fx is vanishing in our assumption. And this is 1. This is not exceeding 1. Remember? Modulo of this complex number exponential is equal 1. So it is not exceeding 1 by module. So, but second function, because we have product, second function is increasing, decreasing. It's going to 0. Right? It's vanishing, 0. Now, the result will be equal just minus infinity to plus infinity fx exponential iota alpha x. Now I get differential alpha d. Differential of exponential iota alpha x. Now I will differentiate this exponential. If I differentiate from derivative, I will get iota alpha. Then iota alpha I can write outside of integral fx, so derivative of exponent is exponential dx. So if you look at this integral, this stuff is actually f alpha, right? It's a Fourier transformation of function f. So which is equal minus iota alpha f alpha, right? So what we proved the following. If you have a derivative function, if you want to find Fourier transformation of the derivative, then it is equal minus iota alpha f alpha. F alpha is Fourier transformation of original function f. Clear this formula? Okay. And now, what is the impact of Fourier transformation for second derivative? If we suppose, let's say, fx and f prime x both are vanishing, at infinity, at plus and minus infinity. Then, if you apply this to second derivative, what will happen? Fourier transformation of second derivative. What is when Fourier transformation is killing one derivative, it is the Fourier transformation of function, right? So for second derivative is the derivative of first derivative. So I can write it like this, minus iota alpha. I'm using this formula for the function, not f, for the function f prime. Because if instead of f, you consider f prime, then it will be f double prime, right? So it's equal Fourier transformation of f prime. One times I use this formula. So Fourier transformation of second derivative is equal minus iota alpha Fourier transformation of first derivative. Now I will use again the same formula. Now for first derivative, right? Which is equal. So what will be? Minus iota alpha times minus iota alpha, so means quadrat of this, right? So F alpha. Clear? Now, if you compute this iota square is -1, it is minus alpha square F alpha. So we prove the following. We prove that action of the Fourier transformation to the second derivative is equal just multiplication to alpha square F alpha. So what job done by Fourier transformation? It is killing both derivatives with respect to x. Okay? Okay. Now let's say I have a function u, so we will apply this Fourier transformation to the solution of PDEs, partial differential equations. So we will deal with functions of many variables, not single variables. So let's say we have a function uxt or uxy, it doesn't matter, uxt. Now let me act Fourier transformation on this function with respect to x. So Fourier transformation of uxt, if I am applying with respect to x, so result will be a function of alpha and t, right? T, no changes, right? Then it is equal, by definition, it is equal integral from minus infinity to plus infinity, right? uxt exponenta iota alpha t, sorry, iota alpha x dx. So this is the application of Fourier transformation to the function of two variables, but we are applying Fourier transformation with respect to one particular variable, which is x in this case, which is x. Okay. Now let me denote this by u capital. U capital is a function of alpha and t. So what's job done by this transformation? If my original function uxt, then this transformation is transforming this u into u capital alpha t. So what happened? This transformation, u is transforming to u, right? X is transforming to alpha. No changes for t. U is transforming to u capital and x is transforming to alpha. Clear? Now, what will be impact of the partial derivatives? For example, if I want to apply Fourier transformation to uxx, then what will be the result? The result will be like this, right? We know what is the impact, minus alpha square minus alpha square u capital. Clear? No derivative, so it's killing derivatives with x. If you act on first derivative with respect to t, for example, nothing will be changing. It is just u t. Clear? ut. So your function uxx xt in transformation, Laplace transformation, in Fourier transformation, what's going on with this in Fourier transformation? It is changing to alpha square v. It's changing to minus alpha square u alpha t. So you can see derivative is derivative. Change it to minus alpha square. X is changed to alpha and u is changed to u capital. And you can see t is not changing because transformation is with respect to x. Clear? In previous classes, when we studied Laplace transformation, we used transformation with respect to time. Now we are using Fourier transformation. We are using with respect to position. The same. If you have a function ut xt, and you image, Fourier transformation is just ut alpha t. So no changes for t. T is the same, right? Derivative is the same, and this t also the same, because transformation is respect to x. X is changing to alpha, right? And u is changing to u capital. That's all. Okay, let's see some exercises. Exercise 1, let me take, maybe it's difficult to get a copy, but I will try to get a copy. Okay, let's say this exercise, copy. Okay, this is heat equation, right? Heat equation. Heat equation, we should call this problem like this. Heat equation, heat conduction. Heat conduction in unbounded rod. Of course, unbounded rod physically not exist, right? We have finite resources. I say unbounded rod because it's actually x is from minus infinity to plus infinity. When you have such a problem, rod, of course, we know that rod is bounded. Let's say this is a rod, length is equal L. And of course, in order to study heat conduction rod, you must know initial condition plus two boundary conditions, right? Because it has two boundaries. Whatever boundary condition, let me just consider the following problem. My investigation, my research is focused, let's say, on this part, in somewhere in the middle of the rod, right? And I want to make experiment during 5 seconds. Okay? So what will happen? Will be any influence of boundary conditions? No. Boundary condition will have some impact in the middle, of course, but it takes time, right? Maybe not 5 seconds. Maybe it's less than 5 seconds, right? So it means boundary condition plays no role. We don't need a boundary condition. Then we suppose that boundaries are very far, very far. The 0 and L is very far from the object which we study, which is just middle of the rod. So we can say these boundaries are somewhere in infinity, and whatever boundary condition we are not interested because they have no impact, no influence in the middle, in a very beginning moments, right? Very beginning moments. Of course, it takes time. So then no role play by boundary condition. What we say, x is from minus infinity to plus infinity, then we call it unbounded rod. Then initial condition, of course, important, right? Initial condition, of course, important. Now, let's solve this problem. So problem has only equation and one single initial condition, right? So let me transform equation. My equation is ut is equal k times uxx. So what will be the transformation of this in Laplace transformation? In Fourier transformation? Ut is transforming to u capital T, right? K is a constant. Uxx is transforming to minus alpha square. U, that's all, right? Ut is equal k times minus alpha square u. So this you can write like this. Ut plus k times alpha square u is equal 0. What is this equation? This equation is equation 1.2, lecture number 1. It is actually second equation which we have seen, revised in this course. So what will be solution of this equation? Solution is u alpha t u alpha t is equal some constant, let's say a exponential minus k alpha square t. In order to find a, I needed to use initial condition. So use initial condition to find a. Okay. Now for that we needed to transform initial condition. What was the initial condition? U0x is equal to fx. ux0 is equal to fx. Then transformation of this in Fourier transformation. So u0x will be transformed, u will be transformed to ux is transformed to alpha, t no changes, t is 0. So what is the transformation of fx? Fx is given, right? It is a box function. And as exercise, we found above its transformation, right? So then this is equal to u0 sine alpha over alpha. That was the transformation of box function. So u alpha t is equal a times exponential minus k times alpha squared t. From the other hand, u alpha 0 must be equal to u0 sine alpha over alpha. Then I can use this expression of solution with a and find from here a. So what is the u alpha 0? What is u alpha 0? It is a times exponential 0, because when t equals 0, I got here exponential 0. Exponential 0 is 1, which is equal to a. So if I compare both, a must be equal to u0 sine alpha over alpha. Clear? Good. Now I can substitute this a to the solution. U is equal, u alpha t is equal a, which is a 2u0 sine alpha over alpha exponential minus k alpha square t. K alpha square t. Okay. So this is the image of the solution, but my solution is not this far, right? I have an image. I needed to find u. Look me right here. I needed to find uxt. But I know u capital XT, which is the image. I know the image of the solution. I needed to restore the solution. For this, I needed to apply Fourier inverse transformation to function u capital alpha t. Right? U capital alpha t. So if you apply by the formula, it is what? It is 1 over 2 pi integral from 0 to infinity to u0, which is constant I can write outside, sine alpha over alpha, exponential minus k times alpha square t, exponential minus iota alpha x d alpha. D alpha. Right? This is by definition of inverse transformation. So this we can write like this. It's equal 2 and 2 cancel, u0 over pi, integral from 0 to infinity, sine alpha over alpha, okay, exponential minus k square, k alpha square t, exponential minus iota alpha x dx. Now we can use formula above, Euler's formula above for exponential minus iota alpha. We replace this with cosine and sine using Euler's formula, which is equal u0 over pi integral from 0 to infinity sine alpha over alpha exponential minus k alpha square t. This one I will replace with cosine alpha x minus iota minus, because of this minus, sine alpha x. Okay, d alpha. Now I have two integrals, one with cosine and another one with sine. u0 over pi integral from 0 to infinity sine alpha over alpha cosine alpha x exponential minus k alpha square t d alpha minus u0 over pi integral from 0 to infinity, or sorry, from minus infinity. Yeah, this is integral is from minus infinity to plus infinity, right? Okay. From minus infinity to plus infinity. Okay. Second integral will be sine alpha over alpha, sine alpha x, exponential minus k alpha square t dt, sorry, not t, dx, d alpha. Okay, d alpha. D alpha. Now I will count these functions. So this cosine is even function. Alpha square is even. Okay, alpha is odd. And also sine alpha is odd. Odd over odd will be even. So functions will be even. Then total will be even. So this total function is even. When you have even function and integral from minus infinity to plus infinity, you can reduce it into integral from 0 to infinity. It will be two times integral from 0 to infinity, say function sine alpha or alpha, cosine alpha x, exponential minus k alpha square t d alpha. Okay? So this integral is equal to 0 because this is even. This function is even. This function is even. And this sign is even, odd, or sorry, this is odd. This sign is also odd. It's odd. And alpha also odd. I have product division of three odd functions, then it will be odd times even is odd. So this is 0. So integral by symmetric domain from odd function is 0. So result will be just this one. We will leave answer. Okay, any questions? So from where this appears? Okay. Now let's go to another exercise. So we leave answer like this, integral form, because you cannot evaluate this integral. Okay. Now, let me bring another exercise. Exercise, copy and paste. This is about wave, right? This is a wave propagation or wave equation. Wave problem. For the unlimited or unbounded string. This problem is about vibration of unbounded string. The reason is the same why we consider unbound. So means we are investigating the part of the string which is very far from boundaries. Whatever boundary conditions, the influence will come later. So it has no sense for this problem. Okay. So how we solve this? How we proceed with this? First, we needed to transform equation. Equation is UTT is equal a square UXX. This is the equation, right? When you transform this equation using Fourier transformation, UTT is changing to be UTT, U capital TT, is equal a square minus alpha square, a square from transformation. I got alpha square. UX, U, just U, right? This is a transformation of second derivative to X. Then this equation I can rewrite like this, UTT plus alpha square a square, U is equal 0. This equation we know from lecture number 1, right? This equation is, if you want, you can see this equation 1.8 in lecture number 1. In lecture number 1. So solution of this U function, U capital function of alpha at t is equal, alpha at t is equal A times cosine alpha a t, right, plus B times sine alpha a t. So alpha a t. Okay. To find AB, we use initial conditions. To find AB, find A and B, we will use initial conditions. We have two initial conditions, right? First is ux0 is equal to fx. ux0 is equal to fx. ux0 is equal to fx. So if you transform this equation, u is changing to be u capital, x is changing to alpha, t no changes, t0 in both sides. So what will be this fx? Fx, its transformation is f capital alpha. Whatever f, give me your f, I can find for you, it's Fourier image, right? Then another condition is utx0 is equal to gx. Then if you apply transformation, Laplace transformation for both equalities, then will be, so ut alpha 0 is equal j alpha. Clear? J alpha. Now I can find, this is my u, so what will be u? You can see u alpha 0. U alpha 0 is equal to a, because when t0, sine 0 is 0, cosine is 1, it's equal to a. Just u alpha 0 is equal to a. So a must be equal to f alpha. The same, if you find ut, what is the ut alpha t? Ut alpha t is equal A times, so what is it? This is solution, alpha AT, right? Cosine alpha AT. Minus A times alpha T, sorry, not alpha, alpha A. Alpha A from derivative, right? Then derivative of cosine is sine, alpha AT, plus B, alpha A, cosine alpha AT. This is just simple derivative of function U alpha T, is U alpha T. Its derivative is minus A because derivative of cosine minus A, sine, cosine will be sine. Then from derivative you have additional alpha A. Okay. Now I will substitute into the condition UT alpha 0 is equal to Gx, right? G alpha, right? G alpha. So if you substitute T equals 0, so first term is vanishing, you will get B alpha A cosine 1. Cosine 0 is 1, right? When T is equal to 0, cosine 0 is 1. So this should be equal to G alpha, right? This should be equal to G alpha. So then you can find B. B is equal 1 over alpha A times G alpha. Now I can substitute G and A into the equation solution, then I can find solution of each function, right? U alpha T is equal B equal to this, right? 1 over alpha A, G alpha, G alpha, sine alpha AT, right? Sine alpha AT. This is right. Not this, above. This one. Right? U alpha T is equal, A is 0 already, B is equal this one. So J alpha T. Sine alpha A alpha T. Okay, sine A alpha T. So this is a U. Now what is a U? Our function UXT, which is the solution of this problem, is equal 1 over 2 pi, right? I forget on the previous time writing to 1 over 2 pi. Yeah, I forget. Integral from minus infinity to plus infinity, right? U is U. 1 over alpha A, G alpha, right? G alpha. Oh, F alpha is not 0. Yeah, A is not 0, right? A is equal to F alpha. So I have here F alpha times cosine alpha AT, right? F alpha is not 0. If F alpha will be 0 if F is 0, okay? G alpha sine alpha T exponenta minus iota alpha x d alpha. Then plus 1 over 2 pi. Now A coefficient is F alpha cosine alpha T, alpha AT, exponenta minus A alpha x d alpha. So this is the solution. So you give me your functions f and g, then we can evaluate this integral using given f and g. Okay? Yeah, let's solve one more problem. Let me copy and bring one more problem. Let me bring here one more problem. Control V. This is about steady state. We should call this problem because you see, we have steady state temperature in infinite strip. So this infinite strip, x is from minus infinity to plus infinity, right? But y is from 0 to 1. This infinite strip, mathematically you can express like this, from 0 to 1. And you will get this strip, right? So they say use this formula. So it's given, this is given. Given that Fourier transformation of function exponential minus x square over 4 rho square is equal to root of pi to root of pi to root of pi rho exponential minus rho square alpha square. They give this formula, say use this formula to solve this problem. Let me write first mathematical model of this problem. Let me close the window. I think it's raining. Let's first write mathematical model. What is the steady state equation? What is the equation? Steady state equation is uxx plus uyy is equal to 0. This is the equation, governing equation, right? So then look at this picture, what they say. We have only boundary conditions, right? So they say when y is equal to 1, u is equal to this, right? So u x1, so when y is 1, you see, when y is 1, it's equal exponential minus x squared. This is given. So this side is insulated. Insulated means heat cannot move on this line up or down. Cannot move up and down from this line, right? So how we express this is uy, derivative, no change of function means derivative is 0, right? Uy x0 is equal 0. It's actually insulated. Okay, so this is problem. Now I have a mathematical model. A mathematical model of the problem. Now I can solve this problem using Laplace transformation. Fourier series will not be helpful here. So, okay, let's apply Fourier transformation for the equation. First, equation. Equation is uxx plus uyy is equal to 0. Now, if I transform this using Laplace transformation, what will happen with uxx? Uxx is going to be minus alpha square u, right? Laplace transformation is killing derivative with respect to x. The result will be minus alpha square u plus what will be transformation of uyy. So Laplace transformation is, Fourier transformation is nothing to do with y. So no changes, right? So it will be uyy is equal 0. Transformation of 0 is 0. Now, new equation for image function is this one. If I rewrite this first derivative, uyy minus alpha square u is equal to 0. This is exactly equation 1.8 in lecture number 1. So we know the solution because now you see now it's negative. So now what will be u? uxy is equal 8 times, okay, uxy is equal 8 times cosine hyperbolic. I think we need to use hyperbolic functions. Cosine hyperbolic. So what will be this? Alpha y, because this is minus alpha square, plus b times sine hyperbolic alpha y. Just you look at lecture number 1 and you can see solution is like this. Here's the variable is y. Okay, now to find a and b, we needed to use initial conditions. To find a and b, we use boundary conditions. We have two boundary conditions, right? One boundary condition when y is equal to 0, right? When y is equal to 0, what we have? One is uy. We need the uy. What is uyxy? Uyxy is equal. What's the derivative of this, right? This is alpha a sine hyperbolic alpha y plus derivative of sine is cosine alpha b cosine hyperbolic alpha y. Right now, what is the uy x0? Uy x0 is equal so alpha b, right? Alpha b, because sine is 0, cosine is 1. So uy x0, so what is the uy x0? It is equal to 0 because it is insulated, right? Uy x0 equals 0. So from this we find b coefficients are 0. So if b coefficient is 0, then my function u capital has the shape uxy is equal 8 times cosine hyperbolic alpha y. So in order to find a, I needed to use another initial condition. What is the second initial condition? Right? Second initial condition, ux1 is equal ux1, so it's not x, sorry, this is alpha, right? Alpha. Okay. Alpha. U capital is function because we transform it's alpha already. Okay. Our condition is u x1 is equal exponential minus x squared. Then what will be transformation of this Fourier transformation? U is changing to u capital, x is changing to alpha, t is no changes, 1 is 1. No, y is 1 is 1, right? So equal transformation of what? Exponential minus x squared. We needed to find what is the transformation of this function. For this they give this formula. So my original function is exponential square. What is rho? For this function, exponential minus x squared, what is rho? Rho is equal 1 over 2. You see? When rho is 1 over 2, you will have here 1 over 4. 4 will cancel. Result will be exponential x squared. Then what will be its transformation? 2 root of pi, 1 over 2, Then 1 over 2 is 2 cancel. Then you have here 4 alpha square. 4 alpha square. So then u alpha 1, which is transformation, using formula above, it is root of pi exponential minus 4 alpha square. 4 alpha square. I just use this formula. Okay. Then we can find what is the u alpha 1. U alpha 1 is equal, so what is u alpha 1? It is cosine alpha, right? It is a times hyperbolic cosine alpha. So this should be equal to root of pi exponential minus 4 alpha square. Then you can find a. A is equal root of pi exponential minus 4 alpha square, okay, over cosine hyperbolic alpha. Then you will substitute this a here, you will find the solution. So solution, image of solution, u alpha y is equal root of pi exponential minus 4 alpha square cosine hyperbolic alpha y over cosine hyperbolic alpha. Then we can find u. What is the u? uxy. Now inverse transformation is 1 over 2 pi, right? So result will be 1 over 2 root of pi, because I am taking into consideration this root of pi. Integral from minus infinity to plus infinity cosine hyperbolic alpha y over cosine hyperbolic alpha exponential minus 4 alpha square times exponential minus iota alpha x d alpha. So this is the solution. Any questions for the solution?
No, sir.
Okay, if no questions, that's all for today's class. Let's go for our attendance business. Where is the PDE? PDE attendance section 1. Oh, it's wrong year. This is 2025. Class semester 2 PDE attendance. Okay, section 1. Okay, let me stop. Different things. Stop recording. Stop recording.